Alright, so today we're going to have a look at some further induction questions and some harder questions that are hopefully going to prepare yourself for our task 1, which is coming up at the beginning of 2024. Okay, so the first question we're asked, and we notice that this question, it's an induction question. I haven't stated that it's an induction question, but it's an induction question involving sigma notation. So this type of notation often can be used in induction questions, and it helps us write things in a quicker way, but really it just means, this just means 1 cubed plus 2 cubed plus 3 cubed plus ... plus n cubed. That's all that means. Now the problem with this induction question is we've got a sum both on the left hand side and a sum on the right hand side. So what we're going to do in this question is we are going to have a look to see whether we can summate the right hand side. Now we'll notice that the right hand side of this induction question is an arithmetic sequence. So here there's an arithmetic sequence. We're starting at 1 and we're going to n, and we might note that the sum of an arithmetic sequence from n equals 1 to n equals n is n on 2 a plus l, where a is the first term and l is the last term. Now if we're plussing numbers from 1 to n, there's going to be n numbers on 2. The first term is 1 and the last term is n. So the sum of this arithmetic sequence is n on 2, 1 plus n. Now the right hand side of this arithmetic sequence we can see is all squared. So we're going to square all of that, and we're going to get n squared on 4, n plus 1 squared. So we're actually trying to prove that the sum from r equals 1 to n of r cubed is equal to n on 4, n plus 1, n squared on 4, n plus 1 squared. Right. We all know that the first step of mathematical induction is to prove true for n is equal to 1, so let's do that. N is equal to 1. The left-hand side is equal to 1 cubed, which is 1, and the right-hand side is equal to 1 squared on 4 times by 1 plus 1 squared, which is 1 on 4 times 2 squared. 1 on 4 times 4 is 1. So therefore, true for n equals 1, as the left-hand side is equal to the right-hand side. Okay, the next step is to assume true for n is equal to k. So we've proven true for n equals 1. Now let's assume true for n is equal to k. Right, so we're going to assume that the sum from r is equal to 1 to n of k cubed is equal to 1 of k squared on 4 times by k plus 1. Right, so that is our assumption there. We might note that this means it's 1 cubed plus 2 cubed plus 3 cubed plus ... k cubed. I think there should be a k there. Plus ... plus k cubed is equal to k squared on 4 times by k plus 1 squared. So that is our assumption there. The next step in mathematical induction is to prove true for n is equal to k plus 1. So we're trying to, let's write our goal. Our goal is to prove that the right-hand side is k plus 1 squared on 4 times by k plus 1, which is k plus 2, and then we're squaring that. So let's find an expression for k plus 1. It's going to be 1 cubed plus 2 cubed plus 3 cubed plus ... plus k cubed plus k plus 1 cubed. Now by an inductive assumption, by our inductive step, this is equal to k squared on 4 times by k plus 1 squared, and that's by our inductive assumption. So we can replace that whole expression with what we've assumed is true for n is equal to k. So we're going to replace this with k squared on 4 times by k plus 1 squared plus our k plus 1th term, k plus 1 cubed. Now when we get to this step, it's always useful to consider where we're going. So let's look at our goal. Our goal, we've got a 4 out the front and a k plus 1 squared times k plus 2 squared. Now at the moment we mightn't be able to see where k plus 2 squared comes from, but we can definitely see where k plus 1 squared comes from, and that would be by taking out a factor of k plus 1 squared. So if we take out k plus 1 squared from the left term, we're left with k squared on 4, and if we take it from the right term, we've got 1k plus 1 left over. Okay, now if we do a bit of cross multiplying to get a common denominator, we can times the 4 up to there. So k plus 1 squared times by k squared plus 4k plus 1, and that's all over 4. We've made a common denominator. Because we've got a common denominator, we can pull it out the front, and that gets our k plus 1 squared on 4, which is what we were after, times by k squared, let's expand those brackets, plus 4k plus 4. Okay. This is really good here because that is actually a perfect square. So we can say this is k plus 1 squared on 4 times by k plus 2 all squared. And we might want to finish off and say, okay, therefore this is k plus 1 squared on 4 times by k plus 1 all squared. So we can see that we've really substituted k plus 1 into that expression. So therefore, true by induction for all positive integers n. Okay, question number 2. This is one of my favourite questions because we actually have to do induction twice in this question. And it's something that I'd never really seen before, and when I came across it, I really enjoyed doing it. So we're required to prove that 3 to the power of 2n squared minus 1 is divisible by 8. So we know with these divisibility questions, we have to first of all prove true for n is 1, and then for n is k, we're going to assume it's equal to 8 times by some constant integer, positive integer. So let's first up prove true for n is equal to 1. Let's do that. So 3 times by 2 times by 1 squared is 2. So 2 minus 1, now that's just equal to 8, which is divisible by 8. So therefore true for n is 1. Of course, the next step in induction is always to assume true for n is equal to k. So we're going to substitute k into this expression, so 3 to the power of 2k squared. Let's check, yep, 2k squared minus 1, and it's equal to 8p, where p and k are both some positive integers. Okay, our next step with induction is to prove true for n is equal to k plus 1. Now this is not always the next step for induction. Often, and you'll see these in extension 2, often if we're, say, trying to prove true for odd integers, we will have a different step here. We might prove true for n is 2k plus 1 or 2k minus 1, for example. But in extension 1, I'm pretty sure all the time we're always proving true for n is k plus 1. So we're going to say 3 to the power of 2k plus 1 squared minus 1. And we're trying to prove that it's divisible by 8. Okay. Remember, when we're doing this step, we're thinking, how can I use my inductive assumptions? So we're thinking, okay, I need to somehow get one of these terms down here, and it's probably going to be this term. So we might want to state to the side that 3 to the power of 2k squared is equal to 8p plus 1. We're going to try and manipulate this expression to get this here, and that's what we do always for divisibility tests. We try to rearrange our assumption to plug it into our n plus 1 step. So let's expand that power. So it's 3 to the power of 2k squared plus, it would be 2k in the brackets times by 2, so plus 4k, and then 1 times 4 plus 4 minus 1. Now I can see a 2k squared there, but I can also see something that I'm not the biggest fan of. So let's have a go at expanding it and then seeing what we're going to have to do. So this is 3 to the power of 2k squared times by 3 to the power of 4k plus, that should not be a 4 there, 2 times 1 is 2, that should be a 2 there, pardon me, plus 2. So if we expand this bracket, we're going to get k squared plus 2k plus 1, and then 1 times 2 is 2, and then we're minusing 1. Okay, we're almost there. We've actually got a 3 to the power of 2k squared term now, so why don't we plug that in? So we've got 3 to the power of 4k plus 2 times by 8p plus 1 minus 1, and that's by our inductive step, or inductive assumption. Alright, let's expand that. So we've got 8p times by 3 to the 4k plus 2. Now obviously 8p times 3 to the 4k plus 2 is going to be divisible by 8 because we're multiplying it by 8. But what is not necessarily divisible by 8 is 3 to the power of 4k plus 2 minus 1. Now, what we would want to try and do normally is that once we'd done this expansion, the coefficient of this term 9 times out of 10 would be some multiple of 8. But unfortunately in this case it's not. And there's no way of manipulating this to get anything that's going to be a power of 8. We could bring this 2 down to the 3 and say it's 3 squared times 3 to the power of 4k. But again, 3 squared is 9, which is not divisible by 8. So we can't really do much there. So what we're going to do, and this is where this question gets really nice, is we're going to prove that this expression is divisible by is divisible by 8, and we're going to do that by mathematical induction a separate time. So we're going to prove that 3 to the power of 4k plus 2 minus 1 is divisible by 8. Okay. And we're going to do that by induction. So first step, prove true for n is equal to 1. So 3 to the power of 4 times 1 is 4, plus 2 is 6, minus 1. Now 3 to the power of 6 minus 1. Oh, so 3 to the power of 6 is 729. Now 728 is divisible by 8. So that's equal to 728, and that's divisible by 8. We might state that divided by 8 is equal to 91. So therefore it's divisible by 8. The next step is to assume true for n is equal to k. So assume true for n is equal to k. So we're going to assume that 3 to the power of 4k plus 2 minus 1 is divisible by 8, so it is equal to 8p. Now, we actually had a k in our original expression, so we might just change that constant there and say, what's after k? J. So 4j plus 2 is equal to 8p. And where j and p are some positive integers. Right, the next step is we're going to prove true for n is equal to j plus 1. Okay, so prove true for n is equal to j plus 1. So what we're going to do is we're going to say, okay, 3 to the power of 4j plus 1 plus 2 minus 1. Now that's equal to 3 to the power of 4j plus 6 minus 1. Now we might state over here by our inductive assumption that 3 to the power of 4j plus 2 is equal to 8p plus 1. So we want to try and manipulate this expression to get 4j plus 2 in the power. And it's actually quite easy to do that because we can say this is equal to 3 to the power of 4 times by 3 to the power of 4j plus 2 and then minus 1. That's using our basic rule of indices and stating that, okay, I can take out this 4 and when I combine them, I add my indices, so I would get back to there. Okay, now we're going to replace 4j plus 2, 3 to the power of 4j plus 2 with this expression here. So 3 to the power of 4 times by 8p plus 1 minus 1. So if we expand that, it's going to be 3 to the power of 4 times by 8p plus, now 3 to the power of 4 I'm pretty sure is 81, it is, plus 81 minus 1. I might just quickly add in a new page here. How can I do that? It's here, yeah, here. Okay, so we've got 3 to the power of 4 times 8p plus 81 minus 1, which is equal to 8p times by 3 to the power of 4 plus 80. Now we can take out a factor of 8 and say this is 8p times 3 to the power of 4 plus 10, which is purely divisible by 8. Which is purely divisible by 8. So we've proven, after all of that, we've proven that this is divisible by 8, that expression there. So let's copy that and put it down here. So we'll say, therefore, this expression is also divisible by 8. I-V-I-V-I-S-I, divisible by 8, as it has been proven Awesome. Okay, therefore true by induction. So therefore true by induction for all n belonging to the positive integers. Yeah, so that was quite a unique induction question because we were asked to prove something by induction and we actually had to use two inductive processes to actually get a final answer. Okay, the next question is we're asked to show, first of all, that 1 on n plus 1 factorial minus n plus 1 on n plus 2 factorial is equal to 1 on n plus 2 factorial. Let's write that down. 1 on n plus 1 factorial minus n plus 1 on n plus 2 factorial. And we're going to try and prove that this is equal to n plus 2 factorial. Alright, so we might try and make a common denominator here. So let's make a common denominator of n plus 2 factorial. The reason I've chosen n plus 2 factorial as the common denominator is because hopefully we should know that if I multiply n plus 1 factorial by n plus 2, I get n plus 2 factorial. So this is already my common denominator, so I can leave that there. I can leave that thing on the top there because this is already our common denominator. What we have to do is manipulate this. Now to go from n plus 1 factorial to n plus 2 factorial, I have to multiply it by n plus 2. So I'm going to multiply the top by n plus 2. Now if we simplify that, the n's will die and 2 minus 1 is 1. So it's 1 on n plus 2 factorial. And there we're done, QED. Okay, part 2 is we have to use mathematical induction to show that 1 on 2 factorial plus, what is it, 2 on 3 factorial plus 3 on 4 factorial plus dot 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 plus, what's that, n on n plus 1 factorial is equal to 1 minus 1 on n plus 1 factorial. Okay, and we're going to prove that by induction. Of course, the first step with induction always is to prove true for n is equal to 1. So let's prove true for n is 1. We know that 1 on 2 factorial, that's just equal to 1 on 2. That's our left-hand side. Now our right-hand side is going to be 1 minus 1 on 1 plus 1, which is 1 on 2 factorial. And 1 minus a half, of course, is a half. So therefore, true for n is 1, as the left-hand side is equal to the right-hand side. Alright, our next step for an induction is to assume true for n is equal to k. So we're going to assume that 1 on 2 factorial plus 2 on 3 factorial plus dot 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 plus n on n plus 1 factorial is equal to 1 minus 1 on n plus 1 factorial. Okay, so we're assuming true for n is k. I apologize, so we need to replace our n's with k's. K, 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 and then a k here. So, assuming true for n is k, now we're going to prove true for n is equal to k plus 1. So, again, we're proving true for n is k plus 1, so we're going to write out our sequence, 1 on 2 factorial, plus 2 on 3 factorial, plus dot dot dot, plus. Now when we do these, we always want to write in our kth term, so 1 on k plus 1 factorial, and then our k plus 1 term is going to be k plus 1 over k plus 1 plus 1, which is k plus 2 factorial. Now again, this part of the induction stage is always the same, so we're going to say, okay, this is equal to 1 minus 1 on k plus 1 factorial, and that's by our inductive assumption. So we can say, okay, therefore this expression is 1 minus 1 on k plus 1 factorial plus k plus 1 on k plus 2 factorial. Now we're actually really close to what we were trying to prove in the first part of this question. So we can see that we're asked to prove that 1 minus 1 on n plus 1 factorial minus n plus 1 on n plus 2 factorial is equal to 1 on n plus 2 factorial. So these are very similar to that, except in this expression there's a minus here where there should be a plus, and there's a plus here where there should be a minus. So let's take out a factor of minus 1 from the whole expression and say this is 1 on k plus 1 factorial minus k plus 1 on k plus 2 factorial. And therefore, by part 1 of this question, this is 1 over k plus 2 factorial. And this is by part 1. And this is actually equal to our expression that would have been our goal. So we can see this is 1 minus 1 on k plus 1 plus 1 factorial. So therefore, true by induction. Awesome. Okay, next question. We're using mathematical induction to show that 1 plus 1 on 1 plus 2 plus so on is equal to 2n on n plus 1. Okay, this one I haven't done before, but it's looking like possibly it's going to be a nice question because I'm seeing arithmetic sequences down here. So let's see if we have to use that at all. So again, we're going to prove true for n is 1. Let's do that. Prove true for n is equal to 1. So 1 over 1, that's equal to 1. That's our left-hand side. And our right-hand side is going to be 2 times 1 on 1 plus 1, which is 2 on 2, which is 1. And that's our right-hand side. So therefore, as the left-hand side is equal to the right-hand side, it's true for n is 1. Okay, our next step in induction, remember, is always to assume true for n is k. So we're going to assume that 1 over 1 plus 1 on, what was it, 1 plus 2, plus 1 over 1 plus 2 plus 3, plus dot dot dot, plus 1 over 1 plus 2 plus 3 plus dot 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 plus k is equal to 2k on k plus 1. Let's just check that's what it was. Yep, 2n and n plus 1. So that's what we're going to assume is true. The next step, remember, for induction is to prove true for n is k plus 1. So prove true for n is equal to k plus 1. So let's write out our sequence. Again, we're always going to write out this sequence, and we're always going to include the kth term and the k plus 1th term. So 1 over 1 plus 1 over 1 plus 2 plus dot 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 plus, let's include the kth term, 1 plus 2 plus dot 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 plus k plus 1 over our k plus 1th term is 1 over 1 plus 2 plus dot 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 plus k plus 1. Okay, now again, by our inductive assumption, this is equal to 2k over k plus 1, and that's by our inductive assumption. So we can replace that expression with 2k over k plus 1, and of course we've got this plus 1 over 1 plus 2 plus dot 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 plus k plus 1. Now this is where a lot of people might get stuck, because we've got another summation on the bottom of a fraction, but it realistically is not that tricky. It's just an arithmetic sequence. So let's have a go. 1 plus 2 plus dot 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 plus k plus 1. Well, the sum of that sequence from n is 1 to k plus 1, well, it's just an arithmetic sequence from 1 to k plus 1. And we know the formula is n on 2 a plus l. Now, if I'm going from 1 to k plus 1, that's k plus 1 terms. So k plus 1 on 2. The first term is 1, and the last term is l. The last term is k plus 1. So this is equal to k plus 1 on 2 times by k plus 2. Okay, bringing that all together, we can say that, first of all, we've still got that first fraction, 2k on k plus 1, plus 1 over, the bottom of this fraction is now equal to k plus 1 on 2 times by k plus 2. Now, using our fraction rules, we can bring this denominator up to the top. So we can say this is equal to 2k on k plus 1 plus 2 over k plus 1, k plus 2. Now we're going to try and combine these and create a common denominator. Now we can see that the common denominator has to be k plus 1, k plus 2. And to get that, well, this is already sweet here, so we're just going to write a plus 2 at the end. And to transform this into our common denominator, we have to multiply it by k plus 2. So we've got 2k, the numerator, times by the new thing on the denominator, k plus 2. Now if we have a go at expanding the top, we've got 2k squared plus 4k plus 2 over k plus 1, k plus 2. Now we can take out a factor of 2 from here, and we've got k squared plus 2k plus 1, which is really good because that's now a perfect square, on k plus 1, k plus 2. I might insert a new page. K plus 1, k plus 2. So that's 2 times by k plus 1 all squared over k plus 1, k plus 2. And we can kill one of those with one of those, and we've got 2k plus 1 over k plus 2. Now let's have a look at what our goal would have been. So our goal, substituting in k plus 1, would be 2k plus 1 over k plus 1 plus 1, which is 2k plus 1 over k plus 2. So we're all good, we're done. So therefore, true by induction. So again, that question was interesting because it involved the sum of a sequence, but realistically we can see that advanced content is quite straightforward, so we're not going to stress over it. How many more do I have? 2. Alright. This question we're asked to prove that 5 to the power of 2n plus 1 plus 2 to the power of 2n plus 1 is divisible by 7. Rightio, so let's just start with our first step of induction, which is always to prove true for n is equal to 1. So we're going to prove true for n is 1, so 5 to the power of 2 times by 1 plus 1 plus 2 to the power of 2 plus 1, which is equal to 25 plus 9, I think. No, 25 plus 8, which is 33. Have I done so? Oh, no, pardon me. 125 plus 8, which is 134. Let's just check. 134 divided by 7 is not quite. 133, ignore me. There we go, 133. And that's divisible by 7. So therefore true for n is equal to 1. Okay. Our next step with induction is to assume true for n is equal to k. Assume true for n is equal to k. So we're going to substitute n is k into this expression. So 5 to the power of 2k plus 1 plus 2 to the power of 2k plus 1. And we're going to say this is equal to 7p. So 7 times some constant p, where p and k are positive integers. Our final step is to prove true for n is equal to k plus 1. So prove true n is equal to k plus 1. So we're going to substitute in k plus 1 into this expression. So 5 to the power of 2 k plus 1 plus 2 to the power of 2, and I forgot a plus 1 there, plus 1, k plus 1 plus 1. We'll have a go at expanding some of this. So we're going to have 5 to the power of 2k plus 3 plus 2 to the power of 2k plus 3. And we might state to the side that by our inductive assumption, 5 to the power of 2k plus 1 is equal to 7p minus 2 to the power of 2k plus 1. Now the problem with this question is that no longer are the powers here and here the same. And the only way we can substitute and compare these is if we make these powers the same. And it's actually very straightforward to do that. We can pull out a 5 squared from here and say this is 5 squared times 5 to the 2k plus 1. Plus, we can pull out a 2 squared, I might do black again, 2 squared times by 2 to the power of 2k plus 1. So that's using our exponent rules. We know that when we multiply indices, we can add them. So if I add the 2 with the 2k plus 1, we get our 2k plus 3, so that's all good. Now we're going to substitute this 2k plus 1 into here. So we're going to say this is equal to 25 times by 5 times by 7p minus 2 to the power of 2k plus 1 plus 4 times by 2 to the power of 2k plus 1. Now we're not going to substitute this into both here and here. We only choose one of them. It would be pretty pointless if we chose both, and I'm not 100% sure if it works if you choose both. It probably would, but we really only need to choose one. Alright, so we've got 7p times by 25 minus 25 times by 2 to the power of 2k plus 1 plus 4 times by 2 to the power of 2k plus 1, which is 7p times 25 minus 21 to the power of 2 to the power of 2k plus 1, which we can see is going to be divisible by 7. So let's take out a factor of 7 there. So 25p minus 3 times 2 to the power of 2k plus 1. And that's purely divisible by 7. So, therefore, true by induction. Now again, I'm concluding my inductions very poorly. I've shown you that whole novel of stuff that we have to write when we end inductions, and that's what you are expected to write in exams, so a bit more reasoning than what I've done. So you need to go, okay, therefore it's true for n is 1, and since it's true for n is k, and n is k plus 1, then it's true for 2 and 3, and so on. Alright. Our last question is to prove this long confusing thing. I haven't done this one again, so we're going to explore it together. So 2 to the power of 1 plus 2 plus 2 squared plus 4 plus blah 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 plus 2 to the power of n plus 2n, and it's equal to 2n plus 1 plus nn plus 1 minus 2. Okay, so again we're going to prove true for n is 1. So prove true for n is 1. Well, 2 to the power of 1 plus 2, that's equal to 4. And then 2 to the power of 1 plus 1, 2 squared, plus 2 times by 2 plus 1 minus 2. Now 2 squared is 4 plus 3 times 4 is 12 minus 2. How are we getting 4? 2 to the power of 1 plus 2 is 4. 1 plus... Oh, ignore me. I've substituted this in wrong. So we've got 2 to the power of 2 squared plus 1 times by 1 plus 1 minus 2. 2 squared is 4. 1 times 2 is 2, so 2 plus 2. Have I done it wrong again? So that's a 4 there. 4 plus 2 minus 2. 4 plus 2 is 6, minus 2 is 4. So therefore, as the left-hand side is equal to the right-hand side, it's true for n is equal to 1. Alright, our next step is to assume true for n is equal to k. So we're going to assume that 2 to the power of 1 plus 2 plus, what is it? 2 squared plus 4 plus 2n, so 2k plus 2k is equal to, might move this over a bit, is equal to 2 to the power of 2k, 2 to the power of k plus 1 plus k times k plus 1 minus 2. Okay, that's our assumption there. Our final step is to prove true for n is k plus 1. So we're going to go, okay, 2 to the power of 1 plus 2 plus 2 squared plus 4 plus dot 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 plus, again we're writing in our kth term and our k plus 1th term. So 2 to the power of k plus 2k plus 2 to the power of k plus 1 plus 2 times k plus 1. And we're going to try and manipulate this expression to get something that is true for n is k plus 1. So we're going to try and get something that's equal to our goal. We might write that goal down first. So our goal is to prove that it's 2 to the power of k plus 1, which is k plus 2, plus k plus 1 times by k plus 1, which is k plus 2 again, and then minus 2. So bioinductive assumption, again, this is the same process as always. Bioinductive assumption, we know that this is equal to 2 to the power of k plus 1 plus k times k plus 1 minus 2, and that's bioinductive assumption. So let's replace that with our assumption. So 2 to the power of k plus 1 plus k times k plus 1 minus 2, and we've still got our plus 2 to the power of k plus 1 plus 2 times by k plus 1. Okay, to do this question we're really going to focus on our goal. We notice we've got a minus 2, which we've already got here, and we notice that we've got a k plus 2 here, which we don't have here at all. However, I do have 2 to the power of k plus 1s. Let's write that 2 times by 2 to the power of k plus 1. And we notice we could group in pairs and take out a common factor of k plus 1 from here. So grouping in pairs this and this, we're left with k plus 1 times by k plus 2, which is promising, minus 2. And then, well, using our law of indices, this is just a 1 there, so we can combine that and get 2 to the power of k plus 2. 1 plus k plus 1 is k plus 2, plus k plus 1 times by k plus 2 minus 2, which is what we're after. So therefore, true by induction for all n belonging to the positive integers. Alright, thanks for listening. Hope that makes sense.